surface is not horizontal is called the its shear strength. Okay, liquids and soils in liquid form have virtually zero shear strength, and we've said that if you want to know, the simplest way is if you put that material when the surface is not horizontal, then it will flow away, it will not be stable, so that has zero shear strength. So we consider a block of weight resting on horizontal surface as shown in this figure. So when when I'm explaining that part, have the mental picture of this diagram, so that there is the weight, and of course the block is stable because the reaction is the same as the weight, and also assume there's friction between the block and the surface, so that if you try to move it horizontally, there is some friction, and of course the friction, there's some friction angle, there is some friction angle. So this idea we are going to maybe it's easier to understand with the phi. I think I already told you about this. So we want to bring clarity in this part of how this is related to phi. So of course phi is called the internal friction angle. So with that in mind, the vertical reaction R equals W, and there is consequently no tendency for the block to move, because there is equilibrium. And so now, if a small horizontal force H is now applied to the block, and the magnitude of H is such that the block still does not move, okay, then the reaction will no longer act vertically, but becomes inclined at some angle phi to the vertical. Considering the equilibrium of the forces, first in the horizontal direction and then in the vertical direction, it is seen. So the horizontal, of course, this is a fundamental principle in physics. So here in part A, there's no horizontal force, so the W is the same as the reaction, and so because because the block is not moving, so the W equals R, and so fine, we are at equilibrium. Now when you try to move to apply a horizontal force such that the block does not move, the reaction is not, because here the vertical, the only force applied is vertical, the reaction is vertical. But here we have a vertical force but also horizontal, so the reaction is no longer, if the block is not moving, the reaction is no longer vertical, but in some direction. So I need you to think that this H, if the block is not moving, of course the R is W, the root of W squared plus H squared, okay, if the block is not moving. But now I need you to think, so the friction angle is akin to the alpha value when H is just about to move, you get. So you increase H from 0, so that you have a very clear idea. So you can increase H to 1, 2, 3. So the H will reach a value that this block will just about to move. Now at that point, this angle, that would be the maximum, the friction. Now that for the soil, now that would be like the internal angle of friction. So that's the point actually. That's the idea of friction angle. So you can apply this as long as the block is not moving. But when the block is just about to move, now this angle phi, this alpha, sorry, would be equal to phi when the block is just about to move. So this horizontal force is what is called shear, and of course the normal force is n. So because you already know this, n is just usually sigma, and h is tau. For those of you that remember, we had already established that tau equals c plus sigma tan tan phi prime. So this phi is this angle that we're talking about here. That's the phi. Sigma is the weight, and c is a constant of material property. And we've said reaction would be at a position. Of course, the reaction is the perpendicular, which should be the weight squared the horizontal squared. So I think this is a very basic way to try to make sure this point is understood. So the angle phi is called the angle of obliquity, and is the angle the reaction plane sliding makes with the normal to the plane. If h is slowly increased, I think I already said it, but we go over it to make sure that it is understood. So if h is slowly increased in magnitude, at a stage will be reached at which sliding is imminent, just about the block is just about to slide. As h is increased, the value of alpha will also increase until the sliding is imminent. So O has reached a limiting value phi. So alpha, I think this is not right. So when the block is just about to move, because we've said alpha will increase. So alpha at the point of imminent sliding, alpha will have reached a limiting value a limiting value which is phi. So I think the simplest way to understand this is just think. So the simplest way to is to think of it this way, that this when h increases, the value, this angle also increases. So when the block is just about to move, then this angle has increased limiting value phi. So that should be, I believe, should be clear. So alpha has reached a limiting value phi. If h is now increased still further, the angle of obliquity phi will not become greater at the block, having achieved its maximum resistance to the horizontal movement, will move. Yes, so that's the value we are looking for. That's a phi. So the movement is only limited by to a maximum value phi, and that phi is a material property. So beyond that, if you increase h, the material will have no, the block will have no more resistance, and it will have no choice as a consequence but to move. So that's how to think of the property of these materials. So it's like the strength of the material will have been exhausted, and there's nothing else but to fail. So that's the analogy. So the frictional resistance to the sliding is horizontal component. To the sliding is the horizontal component of R, and as can be seen from the triangle of forces, equals N tan phi, where N equals the normal force on the surface of the sliding. In this case, N is W. As alpha only achieves the value phi when sliding occurs, it is seen that the frictional resistance is not constant and varies with the applied load until movement occurs. The term phi is known as the coefficient of friction. Coefficient of friction. So N tan phi. So that angle would be here. Yes, would be here. So complex stress, or when a body is acted upon by external forces, then any plane within the body will be subjected to stress that is generally inclined to the normal is generally inclined to the normal to the plane. Such stresses has both normal and tangential component, and is a compound or complex stress as shown. So all we are saying is that the inclined stress is a function of both totally vertical and horizontal stress. So basically is another way to put this, that the horizontal stress in this direction so the stress in this direction is basically the result of stress in that direction. So in other words, to get a horizontal stress, you need a vertical stress plus, yeah, that's basically the point, what you're trying to say. So in a very simple way, this is what you're saying. So this a plane that is acted upon by a normal stress only is known as the principal plane. There is no tangential or shear stress present, as seen in the next section dealing with the principal stresses. So if you remember what we'd talked about in the before, that we have major principal stress 1, minor principal stress 3, and then this is the intermediate. So the major principal stress is the maximum, so this is the highest, is greater than sigma 2, which is greater than sigma 3. So this is called the major principal stress, which is acting on the major principal plane, right? This is the minor principal stress acting on the minor principal plane, and this is the intermediate principal stress acting on the intermediate principal plane. So that should be clear. On these planes, the shear stress is zero. In other words, let me show you with the so we plot stress here and the shear. So normally we plot sigma 3 here and sigma 1 and draw a nice circle, more circle here. You can see here the shear stress is zero because it's just on the horizontal axis, the same here. But anywhere else, there is a sigma value there and also a tau value. But at this point, sigma is sigma 1 and tau is 0. The same reason there, sigma is sigma 3 and tau is 0. So these are the in the principal planes, the shear stress is 0. That's the point. So that's what you're trying to say here. So we are going to talk about this in detail. So the principal stress, the normal stress acting on the principal plane is referred to as the principal stress. At every point in the soil mass, the applied stress system that exists can be resolved into three stresses that are mutually orthogonal. The principal planes corresponding to the principal stresses are called the major, intermediate, I think I already said this, and the minor principal planes, and are so named from consideration of the principal stresses that act upon them. The largest principal stress is sigma 1, is known as the major principal stress, and acts on the major principal plane. All right. Similarly, the intermediate principal stress sigma 2 acts on the intermediate principal plane, whilst the smallest principal stress sigma 3, called the minor principal stress, acts on the minor principal plane. So critical stress values obliquities generally occur on the two planes normal to the intermediate plane, so that the effects of sigma 2 can be ignored and a two-dimensional solution is possible. Yeah, so basically we ignore sigma 2, I think I already said this, and always just use sigma 1 and sigma 3. And the reason you can see here that critical stress values and obliquities generally occur in the two planes. So the critical values are just sigma 1 and sigma 3. We are interested in either the maximum or the minimum. So those are the critical values. So for that reason, we can always we can safely ignore the sigma 2. So the more diagram, the more circle, we already said this. Figure 3 shows the so this is typically what we say. So figure 3A shows a major principal plane acted upon by major principal stress sigma 1 and minor principal plane acted upon by minor principal stress sigma 3. So here this is the plane, they're usually orthogonal, so this is the major and this is the minor. So and this is the resultant. So this by considering the equilibrium of an element with the stress mass 3b. So here, so if we take an elemental area, all right, element, it can be shown that on any plane inclined at an angle theta to the direction of the major principal plane, there is shear stress and normal stress. The magnitudes of these stresses are shown in this value. So in any plane, so here this is the so sigma 1 is acting on this surface. So the major principal stress and the minor principal strain stress. So because of this, because these are horizontal, vertical and horizontal forces, will cause some stresses. So there is a resultant that is oriented at theta to the horizontal or to the major principal stress. Now on this plane, we can be proven that there is a normal stress and the shear stress. So I continue to remind you this. We tau equals C plus sigma n tan phi. So the values we are talking about, the sigma n is this one, and the tau we are talking about is this. So then these formula lend themselves to graphical representation, and it can be shown that the locus of stress conditions for all planes through a point is a circle called the Mohr circle. In order to draw the Mohr circle diagram, a specific convention must first be followed. All normal stresses, including principal stresses, being plotted along line OX along line OX. I think we have to show, okay, here. Anyway, this is just an explanation for the Mohr circle. So all stresses are normal and minor, whether they are minor or major, are plotted on the horizontal axis, while the shear stresses are plotted in the vertical axis. While stresses are plotted along the axis or y, for most cases the axis or x is horizontal and or y is vertical, almost 100% of the cases. But the diagram, okay, sometimes it can be rotated, but typically they are vertical and horizontal forces. But the diagram is sometimes rotated to give a correct orientation. Yeah, it's easier to figure to assume they are vertical. Actually, in reality, most of these forces are vertical. The major and minor principal axes are vertical. But sometimes in some certain complicated in situ conditions, the major stresses are not necessarily vertical and horizontal. They are 90 degrees, that's okay, but you find that the major principal axis can be in certain orientation which is not necessarily vertical. So in such cases we can rotate, but the idea is these stresses are in whatever orientation the minor and major principal axis or stresses are 90 degrees from each other. So to draw, first lay down the axis OX and OY, then set off OA and OB along OX axis to represent magnitudes of minor and principal stresses respectively, and finally construct the circle with diameter AB. This circle is the locus of the stress conditions of all planes passing through the point A, i.e. plane passing through A and inclined to the major principal plane at angle theta cuts the circle at D. The coordinates of the point D are normal and shear stresses on the plane in figure 4. You don't need to worry about a lot of things. I think I already explained to this in the previous course. All you need to know that this is sigma 1, not sigma 1, that's sigma 3, and this is sigma 1. The radius of that circle is sigma 1 minus sigma 3 over 2, and then the no, is that the radius? That's the radius. But the center is the center of that circle is sigma 1 plus sigma 3 over 2, 0. So once you know sigma 1, and I already said this in the experiments that we usually perform, you have a value there, sigma 1 and sigma 3. So this, because you know this and you know that, you can easily derive the circle. Okay, so this is some proof which you can check for yourself. So this shows you the relationship. This is trigonometric derivations of the circle. All right, so this is how this actually, this is something that we've done before. So you can follow this in the notes. The relationship now. Of course, if you remember the some rules about a circle, a chord extending to theta at the center of the circle and theta at the there's a ratio. If a chord extends the same angle to theta and theta, some relationship you should know in maths. So you can, based on this, you can prove this relationships. So this is either mathematically, or you can do this graphically. I think graphically should be easier. Some of you insist that the math would be complicated, but I think this is just the angle relations in a circle, which shouldn't be very difficult. So in figure 4, so this is the figure 4, OE and DE represent the normal and shear stresses. So OE and DE, OE is which one? OE is the normal, and DE is the shear stress. So components of the complex stress acting on plane AD, so OE and DE represents these complex stresses in this plane AD. From the triangle of forces ODE, it can be seen that this complex stress is represented in the diagram by line OD. So this complex stress the resultant is OD. Basically, we are saying, so this OE is the horizontal component of the normal stress, and DE is the shear stress. All right. So based on this angle, alpha, the the OD represents the actual value of the complex stress. Now, if you remember, we said that you can do many of these experiments. So you could do another one, and normally up to 3. And this is the alpha. You remember we said that angle alpha here. This angle, as long as you increase this value, this angle will increase to a limiting value phi. So how this is mined when we are trying to so here, so this value in fact will increase, and we want phi when we have a common tangent that touches this. So that is your phi. So you can see how this value increases to a maximum value phi. Okay. So for now we are saying that the complex stress, so this is the horizontal component, the vertical component, and then the resultant is OD. Okay, so whilst the angle DOB represents the angle of obliquity, so DOB, this angle here, oh sorry, I think that's the wrong, yeah, DOB, this one, represents the angle of obliquity. Alpha, okay, that angle should be called alpha, not A. Alpha. So the alpha represents the stress on the plane AD. So the limiting condition, so this is what I was telling you, that if you increase to get the tangent, you get phi. So it has been stated that the maximum shearing resistance is developed when the angle of obliquity equals its limiting value phi. For this condition, line OD becomes a tangent of the stress circle inclined at an angle phi to the axis or x. So OX is that. So figure 5. An intersection point that arises from figure 5 is the failure point plane. Is not the plane subjected to the maximum value of the shear stress. The criterion of failure is maximum obliquity and not maximum shear stress. Hence, although the plane AE in figure 5 is subjected to a greater shear stress than plane AD, it is also subjected to larger normal stress, and therefore the angle of obliquity is less than on AD, which is the plane of failure point. So the issue here, it's not basically the shear stress that governs the failure. Is in fact because as the shear stress also increases, the sigma also increases. So the failure point is governed by the phi, rather than the fact that we have reached a maximum shear stress. That's the point. So strength envelope. So if phi is assumed constant for certain materials, then the shear strength of the material can be represented by a pair of lines passing through origin O and phi. So this is very interesting because we said that this is a circle, but we normally just draw half a circle as maybe here. Okay, this is the practice. However, it can be either half a circle in the negative or in the positive, so it's okay. But it's symmetrical, so either if you go down or up, we are talking about the same thing. So we can talk about plus phi or negative phi to the. So these lines comprise the more strength envelope for the material. In figure 6, a state of stress represented by circle A is quite stable as the circle lies completely within the strength envelope. Circle B is tangential to the strength envelope and represents the condition of incipient failure, since a slight increase in stress value will push the circle over the strength envelope and failure will occur. Circle C cannot exist, it is beyond the strength envelope. So here just explaining. So here circle A, because the limiting strength is phi, so A is quite in a stable condition because the strength is nowhere near the maximum value. Circle B, the limiting strength, which is phi, has been reached, so that's just okay. But anything beyond that is so. If you increase any the circle beyond B, instability creeps in. So, and circle C, because the limiting value is already, that means any circle beyond B, below B can exist, but above B, because the limiting value is already exceeded, the circle C cannot exist. Is there class rep any questions so far? Hello?
Yes, yes,
Yes, you have no question.
yeah, no questions, sir.
Okay, so I think we can take a break for 10 minutes and then resume.
That's okay, sir.
Yeah, okay.
Yes.
So then we talk about the relationship between phi and theta. So DCO DCO in figure 7 is here. DCO is 180 minus 2 theta. I think you know this. The angles in a straight line is 180, so this angle here is 180 minus 2 theta. So in that triangle ODC, angle DOC is theta, so DOC is phi, sorry, and then angle ODC is 90. I mean, because it's a tangent. Then angle OCD is 180, of course. These angles can sub 180, of course. That's no issue. So we get something interesting. The angle theta is actually phi over 2 plus 45 degrees. That's important. This angle is important in failure. Please note this, that angle theta is something very uh, interesting for use later. So just to show you some calculation how to do this, to use all this information that we have. So on a failure plane, a pure fractional mass dry sand. The total stress at the failure shear is 35, and also basically basically what you're saying here on an element like this, the shear, so the normal here is 10 and shear on the same surface is 3.5. So determine by calculation and graphically the resultant stresses on the plane of failure, the angle of shearing resistance of the soil, and the angle of inclination of the failure plane on the major principal plane. So by calculation, the soil is frictional, therefore the strength envelope must go through the origin. The failure point is represented by point D with coordinates 10 and 3.5. So figure 10 is here, figure 8 here. So frictional, some of this is to help you develop the intuition. Because this is frictional soil, pure frictional, you remember this curve that we always talk about. So this sigma. So non-pure frictional soil has a value here, C. I always sing here that this is C plus sigma. Okay, let me write down here. Tau is C plus sigma tan phi. That's what the governing equation here. So this is non-frictional soil because there is a C value. There is a C value there. However, for pure frictional soil, the curves comes from the origin, so there is no C. So here, in other words, we are saying here C is 0. So that should be clear. So then we are simply trying to so by calculation, the soil is frictional, therefore the failure point is represented by point D in figure 8. So here, so this is what we are saying. However, in terms of calculation, the resultant force, of course, is you remember this. The shear is the resultant is 3.5, and this is 10. So the resultant force, of course, is the square root. Should be very easy. The phi is basically the tan inverse of the tangent, basically. So phi is tan inverse of 3.5 over 10, and the theta is can be calculated this way. So that's in terms of calculation. Now in terms of of graphical approach, in the graphical approach, so the procedure figure 8b is first to draw the axis or x and or y, then choose a suitable scale, set off point D with coordinates 10, join OD. This is a strength envelope, the stress circle. Anyway, no need for so many things, except what I'd say is that of course, the circle. Assume you don't know anything here. Whatever they are describing there. So sometimes I'm surprised at the students of today, please, if you have a graph and you are drawing a graph, make sure the rules are still apply. Draw don't get as the corner of the graph and draw a very small minute graph that no one can see anything. All the rules still apply. Graph, choose a suitable scale, make sure the graph covers at least a good portion, 3/4 or 50%. Students of this day, I don't know, and this is what people are taught in high school. That common sense is still because, of course, in university we build on that knowledge. So this basic stuff, no one probably will tell you, but he is expected. So sometimes when we mark, we find very strange things. So this is the shear. This is the normal, which is sigma 1 and sigma 3. But now you here, you don't know anything. You only know that they are 0.103. So 10.3 says here. So, but that is a point on the tangent of the circle. All right. So you know that. So if you want, through trial and error, because you know that at this point is 90 degrees. If we have a circle, the point is 90 degrees. So you can draw 90 degrees. Of course, the 90 degrees can be here. We can also have okay, 90 degrees. Make sure this is 90 degrees. Then when it is 90 degrees, this is the radius of the circle. Sorry, that's the radius. So you use that to draw, and then you can draw your straight line, and then you can know the resultant force. So whichever way, all you need, if once you know the characteristics of that circle, then you should be good. You should have no big issue. So the stress circle is tangential to OD, line perpendicular, and C being the center. So once you draw this, then you can scale. And a good student, after this, you can make sure you can do all this, and you can solve. So with that, the angle phi, we can easily measure. Once you do it graphically, then you can measure the angle phi, and the angle theta should not be very far from these values here. Here we get 54 using calculation. If you do it, you get phi as 19, and 55 should not be very difficult. So good student, please make sure when you go home, you're able to, and then you'll be able, obviously, to read the values at the sigma 1, sorry, sigma 3 here. And once you draw the two trial and error, this one is sigma 3 and that's sigma 1. So I think this is quite simple. So here, and I will sing this. Actually, the point here is this: is to get it in your brain that this is what we are looking for. C plus sigma tan phi, and that for sand, this is the general equation, but for sand this is 0. So tau is C. Sorry, tau is just sigma tan phi, like the case we have talked about just now. So this is all the point, and of course the nitty-gritties about the Mosaic. So it is possible to make the vertical cut in silts and clays, and for this cut to remain standing and supported for some time. This cannot be. So what we are saying here that some of you might. So on normal soils, This is your soil. So in sands, you cannot create as a hole and this remains stable. This can only happen probably in so this wall will remain standing only maybe in clay, in silts, but cannot happen in sand. So that's the point, because the sand has no cohesion. This is what we are saying. So I believe if samples can just stand, you can sample and the sample stands without collapsing. That sample has this thing we call cohesion. So that's what we're trying to say here. That the cut remains standing and supported for some time. This cannot be done in dry sand, which on removal of the cutting implement will slump until its slope is equal to the angle of repose. Again, another something important. The angle of repose has something to do with the phi again. So when you pour something like flour or sand in this case on a flat surface, the it will pour. So these are the particles of sand. You just pour on a free surface. So they will. This angle is what is called the angle of repose. The angle of free standing. So if this is flour or this is a loose soil, so that's what you call a line of repose. So if you try to make a sample like that stand on its own, it won't. It will just collapse. It will collapse until, so this free sample will collapse to that. So you have the angle of repose. So this is the idea. So this cannot be done with dry sand, which on removal of the cutting implement will slap until its slope is equal to the angle of repose. In silts and clays, therefore, some other factor must contribute to shear strength. This factor is called cohesion, and the results. So the fact that it can stand without any support, without collapsing, but so for example, sand, it cannot stand but will collapse and form the angle of repose. So these other materials that can stand like this have this additional factor called cohesion from the mutual existing attraction between fine particles that tend to hold them together. In a solid mass without the application of external force. Yeah, so this idea, you can see the reason why you can pour sand is because they lack cohesion, but you can imagine that also in clay. Clay lump together. That ability to lump together is because of that cohesion, because particles tend to attract each other strongly. So in terms of the Moore diagram, this means that the strength envelope for the soil for undrained conditions no longer goes through the origin, but the intercept axis. See figure 9. So basically, from what it's better to learn from known to unknown. These diagrams will be, so that means this curve will be cutting from there, not from the origin. That's the point. Now let's see this. Yeah, this is the diagram we're talking about. So please, if you have any question, you can interrupt. Yeah, so for the cohesive soil, you can see the difference. The C is so a cohesive soil. Something is not right here. Cohesive soil subjected to undrained conditions and the zero to normal stress will exhibit Cu. Well, I think this is not very right. I need to correct this. Let's just call this U for now, and not CU, because CU is something else. So let's call this C. Yes, just call it C, and then change this diagram to because CU is something else. Copy. So let's just say that's C, not CU. CU is something else. So we can say that so here, so see the figure 9, the values of the intercept at the same scale as sigma n gives a measure. So please note that this curve at this scale has to be the same as that scale. The whereas so the unit cohesion so gives a measure of the unit cohesion and is given the symbol C or Cu. Cu is something else. I think we need to ignore this part. Cu is in fact something else that we will talk about in later discussion. So let's just call it C, not. So C. So then we go to what is called the Coulomb's law of the soil's shear strength, which I think I've highlighted a bit of it. So here, it can be seen that the shear resistance offered by a particular soil is made of two components of friction. The cohesion, frictional resistance, does not have constant value but varies with the value of the normal force acting on the shear plane, whereas cohesive resistance has a constant value which is independent of the value of sigma n. So in 1776, they suggested that the equation, so Coulomb suggested the equation of strength envelope could be expressed in a straight line this way. So I'll try to make it a little clearer. So the first things first, what we are trying to do here is see this block here, the block that we are trying to move. Okay, maybe we go to the actual the previous one. So all you need to understand here that first, this force here, we are saying this force is a constant C, which is independent of anything else, but we have sigma n tan alpha here, which can be phi. So two things, because this is C is constant, so when tau goes up, when sigma n goes up, because phi is also a constant. Phi is just a maximum value, so that means the higher the in fact the shear resistance given by the soil depends on the confinement. So what does this mean in physical terms? This means that if this is the layer of soil, the strength here, strength A, okay, I need someone to tell me. So the height, the Z is increasing. Tau A, tau B, tau C. Which one is higher? Class rep?
This is, I think it's Tau C.
Exactly, because the confinement is increasing. The confinement here, the sigma n here is gamma times a small z, right? Say z1, which is small. And here, so okay, let's say, so here is 5, here is 10, and here is 15. Because the z is increasing, the confinement is increasing, so this the taus must also increase. So that's the first thing we need to learn. Number two, this is the reason why when you are doing the experiment, you vary this. You put a smaller value of sigma 1 here and sigma 3. Sigma 3. So here maybe this is 50 and this is, okay, let's say this is 30. I don't know. So if you draw the first you have a small more circle. Now when you increase this value and say maybe is 100, then you are going to end up with a bigger uh, with a bigger circle. And if you do another experiment with even larger, you'll end up with even a bigger circle, and then you draw a common tangent. So this is the idea, that the fact that when you increase confinement, the shear resistance also will increase due to the explanation already provided. So in a nutshell, this is what Coulomb gave to us. Actually, in reality, this is not exactly the case. In reality, the more circles, if you draw the curves, they are not actually a straight line. So you can have several curves there. No. That may not be very correct or not very accurate. Okay, let me go to the. So in reality, in fact, you can draw several more circles, but they are not that straight. So you can have several. In reality, there is a curve. Is a curve. So the envelopes is a curve. In reality, this is the reality. But because doing curves are of course difficult, the equation itself is difficult. So uh, engineers decided to approximate this to the best straight line, such that this is phi. Yeah. So and the straight line now we say this is tau and this is sigma. Then we are saying the straight line with equation is c plus sigma tan phi. But in reality, that envelope is a curve, more or less. So that's the point I'm trying to derive at. So that's all, the whole idea of Moore of Coulomb, and so this is quite famous. and in fact is the most reasonable. People in the recent years have come up with other failure criterion, but Mokulomb is the most widely used, and in fact even the development of those other models are based on this Mokulomb. It's the most basic. That's the point. So this is the idea, the entire summation in terms of the most general. But when C is 0, of course, it just becomes tau equals sigma tan phi. So that's the basic thing you need to know. The equation, okay, now some technical information you need to know. The equation gave satisfactory predictions for sands and gravels, for which it was originally intended, but it was not so successful when applied to silts and clays. The reasons for this are now well known and are the drainage conditions under which the soil is operating, together with the rate of applied loading, have considerable effect on the amount of shearing resistance the soil will exhibit. None of this was appreciated in the 18th century, and this lack of understanding continued more or less until 1925 when Terzaghi published his theory of effective stress. I think I already introduced this. Now we talk about it in detail. It should be noted that there are other factors that affect the value of the angle of shearing resistance of a particular soil. They include effects of such as items as the amount of friction between the soil particles, the shape of the particles, and the degree of interlock between them, and the density of the soil, its previous stress history, etc. So that's some technical information. For now, all you need to know, I don't know, I think I already talked about this, but here you will read for yourself. But in summary, what I will tell you is basically, which I think I'm sure I already introduced to you. Now, effective stress, because I told you sometimes we cannot measure the pore water, but if we can measure the pore water, then these values, this is now the stress sigma 1 here, would be the total stress sigma minus sigma 1, basic, no, not sigma 1, sigma 1. So let me just be clear. The ones with asterisk on top, the no, not apostrophe, sorry. The ones with apostrophe is effective stress parameter. So this effective parameters takes care of the fact that the pore water. So sigma 1, this is sigma 1, the total stress minus the pore water. Again here, this is would be sigma 3 equals the sigma 3 total stress minus the pore water. The water exerts pressure everywhere the same, so the pore water would be the same. So inside the sample. So this is the modification after of the Coulomb theory, after we knew this, and this was done because you've seen that for sands and silts, this principle used to work just okay. So when you're talking about if a total stress parameter is okay, it just worked okay. And the reason for this also is that sands, in fact, because they have high permeability. So when you try to load it, and even when there is water can flow away easily. So in fact, the effective and total stress parameters more or less give you the same strength properties. However, for sands and silts and clays, the pore water is very small. There's no time for the excess pore water to flow away. So that's why this initial equation it did not work. So if you want to deal with the clay, you have to subtract the pore water pressure. So the same equation, but now expressed in terms of you can see these ones have apostrophe, different from the this one's different from this. Yeah, different from this. So this is the total stress parameter. Now these ones are effective stress parameters. Now you can see here, I think you read for yourself. The only difference here, now we are subtracting the pore water, which you read for yourself in the note. So here we're trying to talk about effective stress, which is basically the effective stress is the total stress minus the uh, minus the 2 p.m. That's yeah. So this is in terms of effective stress parameters. So when you use effective stress to determine those parameters, you put an apostrophe, and the difference is when you're dealing with effective parameters, you have to subtract the excess pore water pressure. So the entire thing. So now there is some difference. So sometimes the okay, let's finish this first. So the shear strength depends upon the effective stress and not total stress. Coulomb's equations must therefore be modified to this. I think I already said this. It is seen that the dependent on the loading and the drainage conditions, the it is possible for a clay soil to exhibit purely frictional shear resistance to act as C is 0 or phi. So C is 0 or phi soil. That means the so C0 is just the what we are saying. So that's tau and this is sigma. So C0 means the it passes. So it's a phi soil. It's a C0 or phi soil. That means it's only about the resistance is only provided by phi. So when it is loaded under drained conditions or to exhibit cohesive, so cohesive, now this is a little not as simple. I'll try to explain. Cohesive to act as phi equals 0 or Cu soil. So phi equals 0. This is something else. See example in 8. So the obviously an interim stage, the clay can exhibit both cohesion and frictional resistance to act as C equals to act as C phi. So now this is so we can have either okay, let me explain to you is here. So there are two things. One, we can have a soil sigma and tau. Okay, so this is phi. So this is called phi. This is C equals 0. C is 0. Or we can just say this is a phi soil because the C0, so that's 1. 2, we can have what we call, and this is why I was telling you Cu is something else. We can have phi equals 0, 0 soils. And what this means is that please pay attention. So this is for sand. Okay. Because sand have good permeability, when you're doing the test, the drainage can occur effectively, and so you can do this. Now for clays, we are saying the soil strength is governed by effective stress. Effective stress, where this equals sigma minus u. Okay. But to measure this, the drainage condition takes time because clay has low permeability. So what is usually done is we don't we do what we call a total stress measurements instead of effective stress. Now for this reason, we assume for saturated clay, we get now for saturated clay, we do what is called undrained test, and what we do is just do at several tests. While under this condition, you can only have what you call SU. So this is called CU. So this is undrained shear strength, quite different from this condition where there is a C here. So this is a CU soil. So for the here, we assume that the phi is 0, and this is usually done for saturated clay. So note that the soil can have these two conditions where we have purely friction soil, where this phi and C here is 0, or have a soil that have Cu and phi is assumed to 0. So those are the extremes. Also in between here, we can have a soil that has both C and phi. So a soil like this, a soil like that. So please note those two conditions. We can have, and this is sand, this extreme condition, this is sand, and actually this is clay. So we can have a phi soil, C is 0, we can have a Cu soil, phi is 0, and we can have a soil in between where there is both C and phi. I think I've tried my best to explain that, to make that clearer. So that's the issue here. That's what this is trying to explain. So a little bit of the more Coulomb yield theory, which we can talk about, and then we talk about the test. So over the years, various yield theories have been proposed for soils. The best known ones are the Tresca theory and von Mises, the Coulomb theory, and the critical state theory. The first three theories have been described by Bishop, and the critical state theory by Schofield. Okay, these are some references. Only the Coulomb theory is discussed in this chapter, and the theory does not consider the effect of strength of volume changes that soil experiences on its way to failure. nor does it change the effect of intermediate principal stress, nor does it consider. Nevertheless, satisfactory predictions of soil strength are obtained, and it's simple to apply. The Mohr-Coulomb theory is widely used and the analysis of most practical problems which involve soil. So, despite other theories being proposed, the Mohr-Coulomb is what was found to fit the soil behavior much better. So, Mohr-Coulomb theory is really an extension of the Tresca theory, actually related to the Tresca theory, but in this case, we will only focus on the Mohr-Coulomb and the aspects that are applicable to the soil, which in turn was probably based on Coulomb's work, hence the title. The theory assumes that the difference between the major and minor principal stress is a function of their sum. Okay. Any effect due to sigma 2 is ignored. The Mohr circle has been discussed earlier in this chapter, and a typical example of Mohr circle is shown in figure 10. The intercept on the shear stress axis of the strength envelope is the intrinsic pressure, i.e. the strength of the material when under zero normal stress. As we know, this intercept is called cohesion in soil mechanics and given the symbol C. Okay, so this is the idea, and of course if you want to know this angle phi is DC, so DC over O prime C. So if this angle, so this is the 90 degrees here from the trigonometric relationships, and I think you can follow this based on the C, and this is you want to express the C in terms of these values. So which is generally so this that C is so general form of the Mohr-Coulomb theory. The equation can be expressed in terms of whether total stress or effective stress. Like I think we have seen the two. But this general agreement that the effective stress because the soil strength is governed more by effective stress. However, because of the issues of the drainage, I think I've also explained to you why we talk about also the phi u and the cu. So determination of shear strength parameters. The shear strength of the soil is controlled by effective stress that acts upon it, and it is therefore obvious that a geotechnical analysis involving the strength, the operative strength of a soil should be carried out in terms of the effective stress parameters phi prime and C prime. This is the general rule, and as you would expect, there is at least one exception. The case of fully saturated clay highly subjected to undrained loading is much more simple to analyze using total stress values and phi u and C than with effective. So because of the issues of drainage issues of the effective stress, we because of the drainage issues of effective stress, we can there are always issues with there are always issues with the effective stress when we're talking about undrained condition. As will be illustrated in later chapters, such a situation can arise in both slope stability and bearing capacity problems. It is seen therefore that both the values of undrained parameters phi u and cu, or simply phi and c, and the drained parameters phi prime, c prime, or phi d and cd are generally required. They are obtained from the results of laboratory tests carried out on representative samples of soil with loading and drainage conditions approximating to those in the field where possible. The test is in general use the direct shear box test, the triaxial test, and the unconfined compression test. which is an adaptation of the triaxial test. So we will talk in detail about these tests, each of them. Of course, they are related to the Moore-Coulomb theories. And okay, we can take a break for 10 minutes, class rep.
Yes, sir.
Okay.
It's okay.
With the class. So usually we some tests, and these are quite important in practice. This is these tests are quite used more often than not. The other tests are derived more or less from this kind of test. So these are the basic tests. So we usually use a direct shear test. The sample is 60 by 60. So this is for granular materials. Now usually when we there's a large shear box for testing gravel or material that are quite has a lot of stones, because the smaller one can be used to test just pure. If you have soft clay or sand that is just pure. But sometimes when you have a large soil with large material like gravel that may destroy a small machine, then we use the bigger. This is called large shear box test. Now you read all those things for yourself, but the idea here is this is the sample, and uh, best you need to think along the theory that we've already established. So this is the sigma, and this is the shear you're applying. All right, so just that simple. So this is the soil you are trying to shear here. So this box is moving, will move over. The top part is moving over like this. No, okay. The direction that we are saying, so that this part will move like that, over that, and this resistance here, that is what we want to measure. That's all. And then there's a normal load here, sigma, and a normal load there. That's the whole idea. Now this is a box. In fact, this the dimension. So in plan, this is what you see. In plan, this is what you see. So it's a box where this is 60, this is 60, and this is also 60. And usually there's a pin to align them. There are pins here. There are pins you put here, two of them here, and also there, and also here and here. Now those pins, just to make sure the corners of the equipment are aligned. Otherwise, when you are doing the test, you have to remove the when you're doing the test, you have to remove the pins. Otherwise, you'll be shearing the pins. So once you assemble, put the sample inside. You assemble, and then you put the pins to make sure the top part and the bottom part are aligned properly. Just before you start shearing, you have to remove the pins. Otherwise, you'll be shearing the pins, and that will be giving you the wrong results. Now, this load is normally known. in theory, in practice is 100 kPa. For the past test, I told you you use a different value, so 100 kPa, then you increase to 200 kPa, then you increase to 300 kPa. Sorry, 300, not 3000 kPa. So at least the standard is 3. Each of this is going to give you a circle. So when there is a gear attached to this, so this force will be given to you straight away, right? And of course here I think is quite simplified, but the idea here is that you will have a straight line. Due to that shearing, you will measure the displacement, and the force, or okay, that's the shear force. So it will be a little, the values will be the displacement, for example, will be very small. Let's say small displacement, but it will reach a point where the displacement will increase. So usually, okay, let me use a different pen here. Usually is a curve like so when displacement increase uncontrollably, then at some point that is your failure point. You will know, depending, you will, because this system is attached to a dial, and so you'll see every time the force is applied and there's shearing, you can see the dial moving. Now it will reach a point where the dial reading will increase uncontrollably. Now that is most likely your point of failure. So when you apply 100 kPa, then you measure the shear force, how much is that, okay? Then when this is 200, again, you measure how much the shear force is, that 300. So each of that will give you uh, three more circle. So this is for the 100, this is for 200, and that's for the 300, from which you can draw a nice straight line, which we've been talking about, touching the tangent. But please note the following, which is important. Here you're measuring, because remember from Mohr circle we are talking only about sigma 1 and sigma 3, but here we are talking about sigma. So what you are measuring is sigma, which is neither sigma 1 nor sigma 3, and tau. From your theory, you know that is just a point on the tangent of the circle, nothing else. So you only have one point. So this is sigma, this is tau. So you only have a point on the tangent of the circle, which is sigma and tau. So through trial and error, you have to draw a circle. So for the 100, you draw half a circle. So that's the first circle for the so for example, if this is 100, if this normal load is 100, so this 100 and the tau you will measure here is just a point on the tangent of the circle. Then you increase it to 200. Again, you measure the tau, a point at just one point at the center, from which you can draw a second circle. Then the third one, then from there you can draw a straight line. Please note that usually confuses people in this test. Something else you have to check is the strain. The strain is the movement. So because the dial will be giving you the the movement, so you can see the movement of the box over the length of the sample. That gives you the strain. Normally when you are dividing the area, because this force depends on the kind of equipment you have, but mostly you measure the force. So to get the force here, to guess the area is usually the force over the area. But please note, this area is changing because you are shearing. Initially the area is just this is 60, so 60 by 60, but at some point the area is being sheared, so it divides itself into two, so it's distorted somehow, which you have to take care of. So what you do with that, you do this area, it's because you are shearing, the area is going to you have to adjust the area. So the area you have to do 1, the new area is A over 1 minus the strain. The strain is this one. Okay, so from there you get the new area, and that's what you use. So for each measurement you have to adjust the area, because at each point you have a reading for the force, the displacement, and then you can get the strain. From the strain you can adjust for the area. In any case, even if you don't adjust, the correct thing is to adjust for the area. In any case, even if you don't adjust for the area, the strains are usually very small, so the area fairly remains constant. But for accurate results, you can adjust the area. That's the most accurate. Actually, for academic purposes, we do expect you to adjust the area. For practice, when the changes in the area are very small, the strain is very small, then the adjustment doesn't have a big difference in the results, to the extent that actually even some books do not ask you to uh, to to ch- to adjust the area. But I think this is important. This what make the difference. So you need to know that that area has to be adjusted based on proper mechanics. So that is basically a description of the that is basically a description of the process. But basically, when you have results like this, it's very simple. In fact, if you are not asked to draw the Mohr circle, then all you need to do is just, this is sigma. Sorry, remember the scales have to be the same, sigma. So 198 you plot, 200 and 139 you plot, whatever, and then you draw a nice straight line from which you can read off here C, and then you can measure the phi there. And then when we ask you to give us the equation, you can tell us C is sigma. You now have to substitute these values here. Sigma, you have to tell us what these are. Tan, phi is the angle you measure from there, which you can easily tell us. So I mean, it's quite simple and straightforward. Now for shear box test, we cannot have effective stress parameters because all we can measure are total stress parameters. Please note, these are porous disc here. This test is usually done underwater. Because you want the weakest condition, the weakest condition is when it is underwater. So all this box is usually flooded with water. All right, but there is no way to measure the pore water, excess pore water. So we are dealing with total stress parameter. So you will see in the solution how this is done. So you need to think. So I think this is also not right. This just use C and U. Phi U. This is I think this author is confusing two things. Just use here phi is 23 and C is 55, because phi u is something else, which I think I have explained to you before. Phi u is actually phi u is usually considered 0. Phi u is 0, but Cu is in a drained condition. So so this is usually what is called undrained. So this is called Cu, which is undrained shear strength. But in this case, the phi undrained is called is 0. Now those are two things. Please also note, okay, maybe this is the case here. Sometimes they depend on the test, because this test is undrained test, all right? So this U here is to show that it's undrained, and from undrained test, all right? Yeah, so that's a bit confusing, because this CU is usually used for what is called UU test, what I have explained here. So please note that difference, and that it doesn't confuse you. So, but in this case now, phi U is 0, and this is called SU or CU. All right. Now, when you do, sometimes there is a phi and a C, but it is from an undrained test. So the U here is used to qualify the fact that those parameters are derived from undrained test. So again, when you use what is called UU test, you get such values with U. So please do not get confused with that. So so this is the solution for that. Now then we have another example which I'll leave for you to figure out by yourself. So this is the strain, and these are the forces for which now you have to change the areas. Okay, I think there's a solution there for you which you have to try to follow. If you're a good student, after this class you have to do that to make sure you can understand. And this is what I was telling you. So I'm not saying this what I'll bring in the exam. So if this thing shows in the exam, I'd be shocked that most of you will fail. And that's why I always tell you, the students of these days, because something like this in the notes and it shows up in the exam. I mean, this is the lecturer is just trying to make you pass. I mean, he's begging you to pass. You see? So if I leave this here and then it shows up in the exam and then you fail, you know? Yeah. So things like this you should as a student, when you go home, you check, because the solution is there, and then you follow. And in any case the lecturer does a mistake in the exam, then you maximize and pass. You see, but this often has happened in the past, and you people are not even able to solve problems inside the notes, which is should be unheard of. So please pay attention. So you see the way it's solved, and because the solution is there, I will not go so much into the detail. Then we have the triaxial test. Now triaxial test is a little complicated, not complicated in terms because the theory is still the same, but complex because we can measure more things. The issues of the dimensions are there. The ratio of the height of the sample to the diameter of the sample is 1 to 2. So the diameter is usually 38 and the height is 76. or in some jurisdiction, the ratio is 100 to 200. So this is, sorry, this is 76. That's 38. So that's in one jurisdiction in the UK, I think, and 200. So in some other jurisdictions, the height is 100, and the diameter is no, the height is 200, and the diameter is 100. So that's about the sample. Yeah. So there's a chamber which is enclosed tightly. The O-rings, because of the leakage and so forth. So the connection between these parts here and here, and even between the sample and the surrounding water, there are some O-rings you put to make sure that it's watertight. Water cannot get inside the sample, and even because you are going to apply a lot of pressure around, which might leak. So sometimes actually you even use oil, not oil, you use grease or ordinary what is called petroleum jelly, just to make sure that water cannot escape, because you're going to apply a lot of pressure. You're going to squeeze the sample. So this is the sample you can see here. Actually, even in certain instances, because water, these things are made by human being. So if the equipment cannot fit exactly on each other, and if because when you're applying pressure, the fluid will find anywhere to escape. So if this happens, because water is quite viscous, we can use oil. Oil is less viscous and a little bit thick, so it's not easy to escape. So sometimes when we cannot use water, we can use, but this is thinking outside the box. We can typically we use water, but in cases you cannot use water, you have problems of excess leakages, you can use oil, because oil is thick. It's not easy for it to relatively is more difficult to escape if you consider compared to water. Now that said, the idea here is that we are applying now I'm going to say a couple of important things. One, this fluid here is applying an all-round pressure. So how does this test work? You apply an all-round pressure, because all this is connected to cell, which you can measure how much pressure you're applying. So in terms of the sample, we have sigma 1, sigma 1. This is the ideal situation of sigma 3. But for the this test happened this way. The fluid will give a uniform pressure, which is sigma 3, sigma 3, sigma 3 initially. Now this sigma 3 must be related. If you remember the consolidation test, I have to get it out of here with to make sure you understand. So the consolidation test, this is the E, and this is the stress. There is a nice curve here. I taught you this because I remember. And then you draw a curve there, draw a curve there, and there's a pre-consolidation stress. So let's call it sigma naught. So normally in this test we make sure the soil is, we say, normally consolidated. We want we don't want over consolidated soil. That means this pressure, this consolidation pressure, has to be at least greater than sigma naught from this test. Must be greater than the pre-consolidation stress from the this is the 1D consolidation test. So please note that is very important. And the issue of the consolidation, if you remember, we said clay has memory. Once it carries 50 kPa today, if that is the load it will always remember. Now, these things will affect the test. So, when you are doing the test, you need to erase the memory. The way to erase the memory is to apply a load higher than the highest load it has ever carried in its lifetime. That's the point. So this consolidation stress has something to do with this pre-consolidation pressure. I don't think there's any other better way to say that. So having said that, so you apply sigma 3 in sigma 3, which should be higher than the pre-consolidation pressure. That's an all uniform stress for some time. That is to erase the memory and make it normally consolidated. After that, you apply something we call deviator stress, delta sigma. So once you apply delta sigma, this becomes sigma 1, and this becomes this sigma 3 remains. All right, because remember, the theory is that this is sigma 1, right? Sigma 1, which can be 100, and this is sigma 3, which can be, say, 50 or 30. And this has load transducers and has sensors that you can see exactly how much you're loading it. Also has some inside the sample has transducers that can tell you how much the pore water pressure is. The idea here now is that if you want sigma 1 prime, you can easily because what you are measuring is total stress, and you are measuring everything, so that would be total stress minus the pore water. Again, sigma 3 would be the sigma 3 minus the pore water. All these values can be derived from the test. All right. So here you have sigma 1 and sigma 3. So, and you can even have the excess so this is telling you the mechanics of the test, which I will. So in the when you are drawing the Mohr circle, so for the first test, depending on the load, so you say the first load. So here, say sigma 1 here is 100 kp, is 100, all right, and sigma 3 here is, say, 30. So that's, you draw your first Mohr circle, then you increase this to 100. You can change this, but normally the idea is to keep it 30. Then you have a bigger circle. Then you increase this to 300. You can change this or keep that support to you. You get even a bigger circle here. And from there you can draw your tangent. So that's the idea. So you can use here because, okay, two things. This test, depending on how complicated it is, you can measure the pore water, excess pore water, or not, or what not. Some of the tests, if the test is not as complicated, then maybe it's not possible to measure the excess pore water. Then that will take you back to the total pressure parameters, just like the triaxial test. I mean the direct shear box test. So this test, because the way it is complicated, results into two things. We can have undrained test, drained test. Undrained usually this, you see this valve here to the pore water. This has a valve that can be closed or opened. So literally drained, because when you are adding the pressure and the sample is saturated, water will try to flow away. So drained means this valve is open. The valve is open. Valve open during the test. All right. Valve open, that, and drained means the valve is closed. Uh, uh, Stay with me, please. So drained means basically that when you are loading, so when you are in, let's say this is the pore water pressure, and this is the stress. Okay, and drained means that when you are, if initially the pore water was here, you are increasing, then the pore water pressure will increase because the water, when you close the valve is closed, that means water cannot escape. If you increase, the pore water will just increase. But when so this is undrained condition. So drained condition means you increase sigma and the pore water is there. Excess pore water can flow away, so the pore water remains constant because the valve, if any case the excess pore water pressure increases, the excess can flow away because the valve is open. So please note that drainage, that condition. Now this test also is done. You have to make sure the you have to make sure the this sample is saturated. All right, these samples you obtained from the soil. They may lose. You want to make sure the sample is saturated with water. How do you do this? You apply what is called a back pressure. Back pressure. Now this has some theory which we will not get into, but the idea now here, when you're applying the sigma 3, the consolidation, well, this is not the same as consolidation per se. You are okay, it's the same, the idea is the same as the consolidation. So sigma 3, but you apply what is called a back pressure. This is a small pressure which is very close to zero, maybe close to zero, let's say, for simplicity. So you apply this. You apply that back pressure for some time, for a few days, if not a few hours, to make sure that water can flow and saturate the whole sample. Around the sample here is almost saturated with water. Now, how to check this has some to do with it's called pore pressure parameters A and B from Henkel. This might be a little bit outside the scope of this work. So this can be done. So you apply that a little pressure, which is close to zero or around there, for some time, to make sure and how will you know the sample is saturated? To check this, after you apply the back pressure, you come to close this valve. Once you close this valve, then you can increase you can give instruction, increase the cell pressure to by maybe say you increase to 50 kPa. You increase to 50. After a few minutes, after 30, a few minutes, the increase in pore water pressure, if the sample is saturated, the increase in pore water pressure should be also around 50 kPa. 50 kPa or at least 45. I think 45 is 90%, or 45 kPa. So the degree of saturation will be delta, not degree. There is what you call the pore water parameter would be delta U over delta P, which if it increases to 45, 50, then that factor would be 0. I think 0.9 or 90%. Or if it increases to 50, that means the parameter is 1, the beta. That means the sample is saturated. Anyway, the idea is the sample has to be saturated before you do the test. So two things. When you do the test, you have to do saturation. You apply the back pressure. I have said for some time, this pressure close to 0. So saturation. Once you saturate, then now you do consolidation. You remember consolidation, you apply all around the issue saturation and consolidation. Here you apply stress close to a value close to 0, not 0 but close to 0. All right. Consolidation, you apply pressure pre-consolidation, some stress, let's call it pre-consolidation, related to the 1D consolidation test. Then now you go, once you finish consolidation, then you can go to shearing. So if you note, in all these instances, in the saturation, sigma 1 equals sigma 3. All right. The same idea here, sigma 1 equals sigma 3. But the consolidation stress is higher than the saturation, the back pressure. But for shearing, sigma 1 has to be greater than sigma 3. So I think I've done a good explanation. So now the cell pressure, which is kept constant throughout the length of the test, it is water. Okay, this you will read for yourself, but it's the same thing that I have summarized in my presentation. Yeah, so that's again here, because you are shearing, you have to check the cross-sectional area. The same idea. So the area will change, and the new area. So if it was 60 by 60, the new area 1 minus the axial deformation, which you can get because you are measuring the changes in length. Yeah, so this is what you'll be told here, the explanation there. So this is the mechanics which you read. I think I've done explanation. I've already explained this. And so this is how to get here the best common. So this is the one you with the small sigma 1. I said normally is 100, and this is 200, and that's 300. So that's up to you. Okay, so you can see this for yourself. So normally this is the sample. You remember we said phi 40. You remember this from the Mohr circle, which I told you is quite important for you to remember. Yeah, the phi, this one, has something to do with. So now that we have reached there, these samples tend to fail at some angle related to 45 plus phi over 2. This is what has been observed, and now you can see the relationship, why that was important. So that's for the triaxial test. So in triaxial test, in fact, this these are the principal stresses, if you remember. These are directly principal stresses, and here the shear stress is 0 and sigma 3. Again, shear stress is 0. That's why you can afford to draw this this, so that this is sigma 3 and this is sigma 1. So please note this is so different from triaxial test, because in triaxial test you only measure tau and sigma, which is just one point on the tangent of the circle, which through a trial and error you have to derive what the Mohr circle is. So that you read for yourself. Then there's another one we called unconfined compression. This is more or less the same as the triaxial test, except now here we have no confinement. So for the unconfined compression test, the strength is 0. So here, you remember, so don't confuse, this is what I was telling you. So here, also we cannot measure the excess pore water pressure. The test is just sigma 1. We don't know, sigma 3 is 0. Sigma 3 is 0. So because sigma 3 is 0, we just have one curve here. And that's so this is SU. This can be called CU or SU. And here we assume phi is 0. Phi U is 0. And it is an undrained test. So that's the issue. That's the point. More or less the a derivation of the triaxial test, as you can see. So you will read for yourself, but the principal idea we've already talked about. So please note this undrained phi, because it's going to confuse you. So this is undrained parameters, which is different from the fact that you are calling it phi u just because you are you are doing undrained test. So please note these two things. So now undrained shear test, I think I already said undrained. All these now are from the test. Undrained simply means you close this valve. Drained means you open that valve during the test, right? I don't know what I needed to now. So during consolidation, remember when you're applying the all-around pressure, the valve is open. All right, valve is open. So saturation, during the saturation, you apply some little back pressure. The valve is also open during saturation, right? Now during the shearing, so when you are calling a test either saturated, I mean consolidated or unconsolidated, depends on whether this valve is open. No, sorry, drained or undrained depends on whether this valve is closed or not closed. That's all. So undrained shear test. So when the box is this is okay. These are the parameters obtained in direct shear box. Also, all right, direct shear box, because we cannot measure the excess pore water pressure. Also in triaxial test, in instances where we cannot measure the pore water pressure. Also in triaxial test when we close the valve. So three situations. Now this test is quite simple, relatively simple and fast, because you don't need to care about the especially in triaxial test, we don't need to care about the drainage. So this, because you are obtaining these parameters from the uh, triaxial test, this is why undrained conditions, this is why you can call this phi u, but in this case the u means undrained, phi u and cu. All right, okay. Please, I'll insist on this. So if you draw sigma and shear, and you just have this from UU test, in this condition, this is also Cu or Su, but in this case phi u is assumed to be 0. These conditions are different. Please note that. So this is some test for you and some solution, how to get the so you should also pay attention to how the solution, how it's solved. So this is the condition I was telling you. So this is normally from what we call UU test, undrained and consolidated test. So you remember this idea that this sometimes the consolidation part is not done. We don't apply. So when you don't when you don't consolidate and you close the valve during the test, then you have what is called UU test. Now this is just an explanation to show you, but the ideal condition is that the test we have the phi u here is assumed to be 0. All right, here because it's too small, in fact, so it's normally assumed that phi u is 0, is approximated as this, and so this is the SU or the CU, and this test is normally called the unconsolidated and drained test, or UU, just called UU test. So the parameters phi and u obtained from undrained testing just called phi u and Cu. All right. Goes without saying that conditions obtained from effective parameters phi. So this is phi u, Cu, or just phi and C, or this is normally sometimes called phi d and Cd when there is drainage. U here stands for undrained and D here stands for drained. So that's it. Those things can confuse you. I hope there's some clarity. So the consolidated and drained testing, I think I've already said this. Testing with back pressures, I've said that. All and so that's everything about the test. The rest you read for yourself. Now there's what is usually called the stress path. I try to explain briefly. The stress path is when you average so you present, okay, it's simply put, when you plot the stress state, you track the stress state and plot in something we call PQ space. So this is the P. This can be P in terms of total stress. So you can plot here total stress or effective stress, and Q. Now that this difference doesn't matter. This we don't we have Q. Yes. Q. There is no Q prime. There is no Q prime. No, this is not there because these differences, sigma V minus sigma H, is the same as sigma V minus sigma H, because the pore water pressure is the same always. So that difference is always the same. But P, there is a P prime because so please note there is no Q prime, but there is a P prime. So if you plot these things in a P or P prime Q space, now that is what you call a stress path. You see what key is a P, but this P can be also this value sigma V. No, this is not right. Discard. this is plus, sorry. This is plus. So if you plot those values in a PQ space with P and Q defined as follows, now that is what is called a stress path, and this was discovered in MIT. And this I'll show you how useful this is in a minute. So if you can track the how the stress changes that condition, that will give you what is called the stress path. And so sometimes you can start from an hydrostatic, okay, or a hydrostatic. So for example, when you start from for example, a point of equal stress, that means sigma. So so this is an isotropic stress. So sigma 3 and sigma 3 is the same. This is called isotropic condition. Isotropic or called hydrostatic. Isotropic or hydrostatic, that means the stresses are the same. You can see here sigma 1, sigma 3 plus sigma 3 over 2 is just sigma 3. But the difference, sigma 3 minus sigma 3 is 0. So you can see why plots at 0. So different, when you apply different stress paths, you have different paths. Or you can have an hydrostatic, which is the truth actually. This is normally sigma uh, uh, sigma 1 and sigma 3, and at this onset condition, sigma 3 is usually 0.5 sigma 1. Now this condition is called anisotropic or anisotropic or non-hydrostatic, as we will see in the next condition. So here the initial condition, the sigmas are different. So this brings me to something we call isotropic consolidation. This means in the process of consolidation, you apply a uniform pressure. Then we also have an isotropic or anisotropic consolidation. This means in the consolidation process, sigma 1 and sigma 3 are not the same. Okay. Then so the importance of the stress path is this. When you sample and you take the sample to the laboratory, this is the path. This is what this is how to track the stress path. So you for example, during sampling, this is the stress condition. When you are drilling, the stress condition changes this way. And of course, how does this related to the failure line, such that this is phi. So this is important to note. And in summary, so different kinds of tests. This is for my own thesis. So different kind of stress paths. And we say P and P because we have effective and total stress. So this is for now that because I have already explained consolidated, isotropically consolidated and drained axial compression test. It means that the consolidation was done with the same uniform pressure. So for consolidated tests, you have to qualify whether there is isotropic consolidation or anisotropic consolidation. Now, there are some tests which are unconsolidated, like I've said, UU, unconsolidated and drained testing. So this word should not confuse you. So here CIU means consolidated, isotropic, consolidated and drained axial compression. Axial compression means that the net effect of the sample is that you are shortening it. All right, axial compression. But there can also be axial extension where where the sample is increasing, and this is achieved through several ways. You can if this value if sigma 3 is higher, if sigma 3 is higher than sigma 1, then you can see this extension can happen, axial extension. So depending on the values of sigma 1 and sigma 3, you can achieve either shortening or extension. Actually, we even have others called lateral extension, where the lateral extension means this sample increases. It's the same as axial compression in a way, where this sample increases in this direction. So, but that is basically dependent. The principal idea is the sigma 1 and sigma 3, but depending on which values. So which one is higher and the combination. So we can either have what is called axial compression, lateral extension, or axial elongation. Now, if you combine all this, whether the test is consolidated and drained, consolidated, this can be consolidated and drained, consolidated, drained. This can also be a CK naught. Let me just. I've said we can have axial compression, axial extension, or lateral extension. Now, each of these tests can be either an isotropic consolidation, which is called K naught consolidation. Yes, someone has a question? Hello?
Yes.
Someone has a question?
Currently, there's no question, but maybe what I can say,
Hmm?
there are some of us who have signed late
No, but I've
because
already
they didn't understand.
who have?
Who have signed late because they didn't understand how to go about it. Yeah,
How to go about the what?
using Google Meet.
Really? They didn't know how to use Google Meet.
Yes, I've advised them, and then they have just signed
Just now.
some few minutes ago.
Okay, I'm just finishing. I'll pick the attendance.
Okay.
So I've said we can have different test: axial extension, axial compression, lateral extension. Now, like I've explained, all these tests can have different kinds of consolidation. Each of these can have, so this can have K naught consolidation or isotropic consolidation. Again, each of these can be done in either a drained or undrained condition. So each of these tests can either one of them, axial extension, can result in 4 different tests. If you multiply by this, you can have 12 different tests. So for example, we can have CIU consolidated Okay, isotropic consolidated and drained axial extension. This is one test. We can have consolidated and drained axial extension. We can have CK naught U AE. We can have CK naught D. So you should be able to be familiar with any of these tests. And what does that mean? Isotropic consolidated means during the consolidation part, you have a uniform stress which is the same sigma 3, sigma 3. And when you are doing the shearing, you close the valve and drained. CID means the consolidation is isotropic. During the shearing, you open the valve. AE is basically sigma 3 is more than sigma 1, so there's axial elongation. That's it. K naught consolidation means during the consolidation, sigma 1 and sigma 3 are not the same. U means the when you're doing the test, you have closed the valve. And so each of these have, for AE we have 4 tests, AC we have another 4 tests, lateral extension we have another 4 tests. So all this can give you a total of 12 tests. So some example which you expected to know, actually these parts you expected to know. So for this CIUAC test, this is the effective and total stress path from my thesis. Now this is K naught consolidation for CK naught UAC, and now you should be very clear what each of these mean. For lateral, for axial extension test, this is the idea. And for drained test, there is no total stress, because the stress is basically effective stress, because the drainage is open, then the excess pore water pressure can escape. I mean, the excess pore water pressure can flow away. So we don't have ideas with excess pore water pressure. So these are different parts, and you're expected to know what they mean. I will send the class rep notes if anyone has any question. And the most important thing in the stress path is to know the expected changes in the stress condition, because this affects the test. Also, this I told you the stress history is quite important, especially for clay, because it always remember if you load it with 100 kPa today, it will always remember in its lifetime. So all these add up to the effective behavior of these engineering materials. Unless there's a question,